Welcome to Pro podcast number 125. And today we're finishing off this two-part series of this podcast talking about the effects of the Reynolds number and turbulence intensity level on a NACA 0018 airfoil. So this is at low Reynolds numbers, and we looked at this paper called Numerical Study of the Effect of Reynolds Numbers and the Turbulence Intensity on the Performance of a NACA 0018 airfoil at the low Reynolds number regime in the last podcast. We're going to cover the second half of this one now. So we'll pick up where we left off. Last podcast, we left off after the validation of this CFD model, which I did a very nice job of, by the way. If you want to look at their CFD validation, which I think a lot of people could learn from, check that podcast out. It's 124, the one just before this. Let's move on with the results. So what are the effects of the Reynolds number on the lift and drag characteristics of an airfoil? This is fairly well covered. However, for a NACA 0018, it's not as well covered because it's fairly uncommon airfoil. Like usually people would go for like a NACA 0015 or NACA 0020. 0018 is not as common in my experience. So they say at a low Reynolds number regime, relatively small differences in this quantity in the Reynolds number can significantly change the lift and drag airfoil characteristics. So let's give a quick background as to why that can happen before we get into the results they found. They say that at a low Reynolds number, so like let's say 50,000, 100,000, 200,000, changing the Reynolds number a little bit can change the lift coefficient dramatically. And the reason why is that if we have the lift coefficient, for example, let's say we have a plot, and for those of you listening to this on Spotify, you can watch the video on Spotify and YouTube. And on YouTube, we have other goodies as well for you if you like aerodynamics. So check that out. So let's say we have a lift curve slope with alpha on the x-axis and the lift coefficient on the y-axis. So if we have, let's say, a Reynolds number of 50,000, which we'll use a black line for, the lift coefficient might look a little bit like this and then start to drop off and then plateau off. Now, let's say we increase the lift coefficient to, the Reynolds number to 100,000, you might get something that looks like this and then drop off a little bit later. Then if we increase it even further to, let's say, 200,000, we'll often get an even greater lift coefficient, the maximum, and then it'll drop off even more. The reason why is because in this regime at higher angles of attack, this is where flow separation is occurring. If we have a low Reynolds number, let's think about what this means. A low Reynolds number means a few things to begin with. First of all, typically it means that we have a higher velocity, and a higher velocity means that we have a higher velocity near the wall of the surface. It could just be an airfoil or anything. If you have a higher velocity near the surface, it means that the flow can stay attached longer. The reason why is because, let me change this color here. Let's say we have an airfoil top surface, so the suction surface as we usually call it. The flow goes over it and we get a boundary layer forming. To begin with, if we have a boundary layer profile, so the velocity as we go up the airfoil, it starts off fairly small, the velocity, and it starts to increase until we get to the 99% of the freestream velocity. As we go over the airfoil, let's say we have a low Reynolds number, so the velocity is quite low. This boundary layer profile will stay largely the same. However, we have an adverse pressure gradient acting on it. So we have this pressure pushing it backwards. And that's not great because if we have a pressure pushing backwards, it means that the velocity near the wall will start to decelerate dramatically and then even reverse. That will result in the flow separating. It comes off. If we have a higher velocity near the wall, so let's say we have the exact same airfoil and we have the same boundary layer profile and we have a higher velocity, so the velocity near the wall is much greater, we have to travel further downstream before this pressure acting back on it can finally make this velocity go to zero and then go backwards and then stall. So that's why at higher Reynolds numbers, that's generally speaking a higher velocity. That will then result in a higher velocity near the surface of the wall, which will then mean that the flow can propagate further downstream before it decelerates completely and reverses direction and stalls. So we can go to higher angles of attack before this happens, because as we go to high angles of attack, the adverse pressure gradient gets stronger and stronger, and that means that the flow is more likely to separate. But if we can jack up the velocity, that's going to delay that stall. That's why when we get a higher Reynolds number, we get a higher maximum lift coefficient. Another reason why a higher maximum lift coefficient occurs is for a similar reason, but not exactly the same. So if we have a higher Reynolds number, what this means is that the inertial forces are greater than the viscous forces, so they're playing a greater role. The higher the velocity, the higher the Reynolds number, the greater the inertial forces are. This is very important because if we have a higher inertial force, it means that any disturbance that comes into the boundary layer, so let's say again we have the exact same airfoil surface, and we have this little disturbance coming into the boundary layer, Now, if you're not familiar with transition to turbulence, check out podcast 123, which we did just like a week ago. I go through in that 4 main ways that bandulators transition to turbulence, and that's actually a really nice podcast that sums up things generally speaking. I do go through this topic quite a lot, but that podcast really sums up quite well. So let's say we have a disturbance coming into the boundary layer. If we have a high Reynolds number velocity, a high Reynolds number flow, sorry, this disturbance will be far more likely to penetrate and really grow inside the boundary layer until it starts to break down 3-dimensionally, and we get a turbulent boundary layer forming. So downstream, we now have a turbulent boundary layer forming. Now, the astute people among you, and to those who don't discredit this picture due to my bad drawing, will realize that the velocity near the wall is much faster when the flow is turbulent compared to when the flow is laminar. That's true. So what this means is if we have a fast moving flow near the wall, again, we can go further downstream before this adverse pressure gradient starts to decelerate to the point where the flow will separate. So this means that the flow can stay attached longer to higher angles of attack without separating. That's why we get a higher stall angle of attack again with higher Reynolds number. So that's a couple of different ways why this happens. And this is what the authors are referring to here. So let's move on to their results. Now, I've gone through that little bit of theory. So let's talk about the effects of the Reynolds number on the lift coefficient here. This is a very interesting paper here. In fact, I'm not even sure if we're going to finish this in podcast number 2. We might need to go to podcast number 3 because there's a lot of juicy stuff here. So all simulations carried out in this paper, regardless of Reynolds number and their turbulence intensity, show a 0 lift coefficient at 0 degrees angle of attack. This is important because this is a NACA 0018 airfoil, and symmetrical airfoils always, unless they're in like ground effect, if they're out of ground effect, they will always have 0 lift coefficients at 0 degrees angle of attack. If they are not symmetrical airfoils or uncambered, I should say, then they will not have a 0 lift coefficient at 0 degrees angle of attack. That is important to note. So that's a good little check if you have your airfoil and it's symmetrical and you get a 0 degree lift angle of attack. So you get a 0 lift coefficient at 0 degrees angle of attack. It means that you've got a good little check there to see that your results are performing as they should be. So in this particular case, in figure 6, as the Reynolds number increases, they show the lift coefficient of this airfoil at 4 different Reynolds numbers: 50,000, 100,000, 150,000, and 200,000 at a turbulence intensity level of 0.25%. This is important. So 0.25% is quite low, and we'll get into higher turbulence intensity levels later. So as the Reynolds number increases, the influence of the laminar separation bubble on the coefficient characteristics decrease, as shown in figure 6. So what do I mean here? So for those of you listening to this, what we can see is a graph. Again, angle of attack is on the x-axis, lift coefficient on the y-axis, and the lift coefficients with different Reynolds numbers are plotted. When the Reynolds number is very low, so 50,000, that's the minimum, at low angles of attack, 2 or 3 degrees, the lift coefficient is much greater actually than any other Reynolds number. So why is this? Well, the main reason why is because of the laminar separation bubble. There's a really good trick you can use to figure out if an LSB is forming on an airfoil just by looking at the lift curve slope. The way that you do this is if the lift curve slope is linear, then you will not have an LSB forming. If it is non-linear, and in particular if it's higher than what it should be, then you will typically be having a LSB forming. So in this particular case, the black line, you can see it's not linear, it's a little bit curved, and it's also much greater than the other ones. That's because of the LSB forming. What this does is, let me come back to our little paint workshop here. Let's say we have an airfoil surface again, the top surface, and LSB is this little region of recirculating flow, and this is separate to the rest of the flow that comes over the top and reattaches back underneath here. So what this means is the airfoil effectively has, let's say this is the front of the airfoil. It's a poorly drawn airfoil, but okay. Let's say this is the thickness of the airfoil effectively now. We have the thickness of the airfoil, the geometry, plus a little bit due to the LSB. So we have a much thicker airfoil now, which results in the lift curve slope being pushed up. Also, it is cambered effectively now because we have a greater thickness on top compared to the bottom. So we have effectively a thick cambered wing now at these low angles of attack. That's why we get a boost in this lift coefficient here. Now, in this particular case, as we get to only even like 4 degrees, the lift coefficient drops, or it sort of starts to plateau for the low Reynolds number of 50,000. And this is probably because at this low Reynolds number, the flow is having trouble staying attached a little bit. It probably also coincides with the LSB popping. So that sort of destabilizes the flow a little bit more flow separation, and then it takes a little bit longer for the flow to reattach. So that's why we start to get more lift being produced at high angles of attack. Now, as we increase the Reynolds number, the low angles of attack start to produce less lift, and this is because the LSB is probably not producing as much lift as where you'd get at lower Reynolds number, sorry. But when we get to high angles of attack, the lift being produced is more stable. So the maximum lift coefficient is greater for the higher Reynolds numbers, which is common, as I mentioned earlier, for those reasons. And also, just generally speaking, the lift curve slope is much more stable. There's not this sudden plateau for no reason, really. So it's better. As expected, as the Reynolds number increases at this low turbulence intensity level of 0.25%, the lift production becomes more stable at high angles of attack too. So that's the lift coefficient with the different Reynolds numbers. What about the drag coefficient? So figure 10 shows the dependence of the drag coefficient on the angle of attack and the Reynolds number. These results are also discussed for one turbulence intensity only of 0.25%. So let's cover this first, and then we'll get into different turbulence intensities later. So in figure 10, the drag coefficient plot shows that at lower Reynolds numbers, the drag coefficient is generally higher, and this makes sense because the pressure drag is higher. The reason why it is higher is because the flow does not have as much energy to stay attached. I went through earlier how the boundary layers develop with higher Reynolds numbers, and so the wake here is a little greater because the flow is not staying attached as well. It has less energy, so that's generally speaking going to increase the pressure drag. Now, I should stress that the wake here is still very small. I mean, the drag coefficient at a Reynolds number 50,000 is still only 0.04 to 0.07, which is still very small, but it is greater than the drag coefficients at high Reynolds number, which are about 0.2 about. At higher Reynolds numbers, the skin friction drag is higher because the flow at the wall is faster. But this small increase in the drag is overshadowed by the great reduction in the pressure drag that you will get at higher Reynolds numbers in this particular case. Also, as expected, at lower Reynolds numbers, the drag coefficient increases sharply at fairly low angles of attack, like 7 degrees. This is because the flow doesn't have much energy, so it detaches at quite low angles of attack. I also think that this is maybe something to do with the LSB popping as well. So I mentioned earlier with the lift coefficient that the LSB started to pop quite early, like maybe 4 degrees, 5 degrees, 6 degrees. This kind of coincides with the increase in the drag coefficient as well. So I think it's partly due to the LSB popping, but also due to the flow separating as well, before it starts to stabilize a bit more. That's why we get such a high drag coefficient at only moderate angles of attack for low Reynolds numbers. Now, this was only for a turbulence intensity level of 0.25%. How does changing the turbulence intensity change the lift and drag coefficients? Let's move on and find out, shall we? So in part 3.2, they go through turbulence intensity effects on lift and drag coefficients. The effect of the turbulence intensity on the aerodynamic characteristics of the NACA 18 airfoil is much smaller compared to the Reynolds number effect. But let's go through and discuss what happens here. While the effects of the turbulence intensity are generally different across the various Reynolds numbers, so we can see here in these graphs, there seems to be one common effect throughout. That is that increasing the turbulence intensity level seems to get rid of the LSB formation, at least for the most part. There is one exception that I'll cover in a second. At the Reynolds number of 50,000, which is around about the lowest Reynolds number that can support an LSB, the LSB is pretty much wiped out with increasing turbulence intensity level. I can tell that from the curve slope here, the lift curve slope here. It is quite linear in this range. If an LSB were present, it would inflect upwards, so the lift curve slope would sort of jump up a bit, but it doesn't. It sort of stays fairly linear and then drops off. At a very low turbulence intensity level, it does a little bit, but I think this is potentially an outlier, or maybe there's just something going on there which they haven't covered here. As the Reynolds number increases, though, the LSB actually becomes quite pronounced as the turbulence intensity increases. As the Reynolds number increases, the LSB becomes more pronounced, and as the turbulence intensity increases, the LSB becomes less pronounced. Why is that? Well, an LSB is a funny formation. It needs the right conditions to form. If it's very fiddly, it's very sensitive. If the Reynolds number is too low, the LSB can't actually form because the disturbances are too low and the viscous effects are too great, so the disturbances get cancelled out before they can even propagate downstream. As the Reynolds number increases, though, these disturbances have a better chance of propagating downstream, which is why when we have a high Reynolds number, the LSB is present at very low turbulence intensity level. So you can see like sort of this Reynolds number of 150,000, 200,000. These lift curve slopes at very low turbulence intensity levels are inflecting upwards. So we're getting LSBs forming here quite nicely. Even the red one, there is a bit of inflection, but it's not as great as the other ones. So now, as the turbulence intensity increases, the conditions are too hostile for the LSB to form. A more direct approach to boundary layer transition takes place. And if you want to check out what I'm talking about, check out that podcast I did a couple weeks ago, that podcast 123, which is called 4 Main Ways Boundary Layers Transition to Turbulence. I'll talk about the other path that turbulence can form in this particular case. But we can see here that the increase in turbulence intensity level sort of drops this LSB effect in the lift coefficient, and the boundary layer transition is taking a different path, at least slightly. So if the Reynolds number and turbulence intensity levels are too low, no LSB will really form. If they're too high, then no LSB will form either. one of the, like either the Reynolds number or the turbulence intensity level needs to be moderate for the LSB to form. They both can't be too high and they both can't be too low. That is why we are seeing such a difference in the airfoil performance here with different Reynolds numbers and different turbulence intensity levels. Now, I should stress that this is CFD, and CFD is notoriously bad for predicting LSBs. However, the general trends found here agree with the literature. So while the exact numbers that we see here are probably a little off, the general trends are good. So let's move on to the drag coefficient now. I just wanted to point that out to make sure that we're on the same page with the CFD's ability to predict LSBs. So in figure 14, the effects of the turbulence intensity level at different Reynolds numbers are shown. Let me zoom out a little bit so you can see the entire thing. Here we go. So one thing that stands out clearly is that at low Reynolds numbers, i.e. 50,000, so this one here, the turbulence intensity has a major effect on the drag coefficient. For example, at 4 degrees, when the turbulence intensity is increased from 0.01% to 0.5%, the drag drops by like 10%. So that's still quite a major reduction, even though we have a small increase in the turbulence intensity level. As the Reynolds number increases, the effects of the turbulence intensity are largely non-existent. So there's a little bit of a reduction, but it's not nearly as much as when we have a lower Reynolds number. But there's a pretty good reason for that, and that is that the turbulence intensity levels are considered here in the study are quite low still. So the maximum level is only 0.5%, which is almost nothing. So at high Reynolds numbers, where disturbances propagate more effectively, changing the turbulence intensity level a little doesn't really make much of a difference. You need to have a higher turbulence intensity level. So if a turbulence intensity level was like 5% instead of 0.5%, then I'm quite confident that we would see significant changes in the drag coefficients even at higher Reynolds numbers. But as it stands, in the turbulence intensity level range typically of most wind tunnels, so here we have turbulence intensities from 0.01%, which is like a really, really good wind tunnel, to 0.5%, which is like a typical wind tunnel. In this kind of range, the drag coefficient is not that sensitive to the turbulence intensity level. It's more sensitive to the Reynolds number at this moderate range of Reynolds numbers. If we were to increase the turbulence intensity level, we would get a significant change in the drag coefficient, as we saw in the lift coefficient as well. In addition to the lift and drag coefficients, they also looked into the static pressure, and this is actually really cool. So we don't get these plots all the time, but when we do get them, they're quite good to look at. They give you a lot of information. So let's cover here the static pressure plots, and I'll describe what they mean in a second. So we have these plots here that range in angles of attack from 2 degrees to 10 degrees, and the turbulence intensity levels range from 0.25% up to 0.5%, depending on which graph you look at. What we have on the x-axis is the distance down the airfoil, so from the leading edge to the trailing edge. On the y-axis, we have the pressure coefficient. So the lower the pressure coefficient, the more. I should explain something else before I go into this. So the solid line is the pressure coefficient on the pressure side, so usually the lower side of an airfoil. The dashed line is the pressure coefficient on the suction side of the airfoil, usually the upper surface. The greater the distance between these two lines, the more lift that is being produced by the airfoil. Now, if the lines are like this solid line, which is the pressure coefficient, the pressure surface coefficient, it should be more positive than the dashed line in order to produce lift. If it's more negative, it means we're producing downforce. So if these lines were flipped, so you have all these solid lines below these dashed lines, then you can say that the airfoil is producing downforce. And a really easy way to figure out how much lift is being produced here, you just integrate the area between these two lines. So you pick out like two black lines, which correspond to the Reynolds number 50,000, and you just integrate the area between them. Or you can do the red line or whatever. So that's a really powerful thing that you can do. Now, figure 18 shows this cool graph of the static pressures over the suction side of the airfoil at 2 degrees. So let's focus on this one here. The other three are quite interesting, but this one's even more interesting. Let me zoom in a bit more. Oops. And for those of you who want to download this paper, I should mention, you can find it in the link in the description. The link to it, it's open access, so you can find it freely. So a clear LSB is visible with the inflection point here. So this point here on the suction surface, and even on the pressure surface, there's an LSB forming as well. When we get these little inflection points on airfoil surfaces with this pressure coefficient, that's a dead giveaway that there's an LSB forming. The reason why this happens is because we have this plateau in the pressure coefficient forming, which is where the LSB is forming, and then we get the sudden drop. That's at the end of the pressure of the LSB. So that's a really easy way of figuring out if we have an LSB forming or not. So that's quite good that they've included this into this paper here. As the turbulence intensity increases, the LSB starts to move forward a little bit. So you can see the black line, which is for a turbulence intensity of 0.01%. It's a little bit further downstream than the red line by maybe a few percent. Now, the reason why this happens is because as the turbulence intensity increases, greater disturbances are introduced. So the disturbances that are propagating into the flow are greater because the turbulence intensity level is greater. So this will be more likely to trigger the path to transition, which hence why the LSB starts further upstream. I should explicitly note that the LSB formation is the onset of transition. So this signifies when the flow is starting to transition. It's no longer laminar, it's starting to transition to turbulence. As soon as we start to see this formation, we know, okay, the bandula is starting to transition now. So having a higher turbulence intensity level is doing exactly what we expect it to do, which is to start to trigger turbulence earlier. And that's why we get this LSB forming a little bit further upstream. Now, if you were to increase the turbulence intensity level even more, I think we'd see this creep up much more to the leading edge. And also at a lower Reynolds number, we'll start to get a little bit more of a spread between these as well. Now, one thing they don't give in this paper is the exact plot at lower Reynolds numbers for the turbulence intensity level, so at 50,000, for example. But I think that the LSB would be affected even more by the turbulence intensity level, or if we had greater turbulence intensity levels here. So we can't see those. They only investigated fairly moderate to low turbulence intensity levels here at sort of moderate Reynolds numbers. So that's the effect of the turbulence intensity level on the airfoil performance. I'll just quickly recap what they are. So we found here that the LSB does form on these airfoils, NACA 0018, and sorry, NACA 0018, and these LSBs move towards the leading edge with increasing turbulence intensity level and with increasing angle of attack as well, just FYI, and increasing Reynolds number as well. We also found that the drag coefficient is somewhat affected by the turbulence intensity level, but only if the Reynolds number is quite low. If we were to increase either the Reynolds number and if we were to reduce the Reynolds number or increase the turbulence intensity level, we would get a much greater effect. And this coefficient is greatly affected by the turbulence intensity level, and it's all over the shop, really. That's because the LSB is greatly affected by the turbulence intensity level, and that significantly affects how much lift is being produced because the airfoil may have like an increased camber, for example, or increased thickness, and that significantly increases the lift curve slope. And then once we get to the stall regime, again, the turbulence intensity level messes with that because it could burst the LSB, could make it not like form properly, and etc. So the turbulence intensity level affects the lift coefficient a bit more of this airfoil than the drag coefficient in this range that we looked at. So that's in this paper. In this podcast, we've covered everything we wanted to cover. That was good. I thought we might need to do 2 podcasts here, but we got it done here. So that's good. So if you want to check out other podcasts, 123 I mentioned was for the boundary layer transitions, and 124 is the prelude to this podcast. And make sure to like, subscribe this. And if you want to get better at CFD and or theory, check out courses in the link description. And if you want to make your experiments 2 to 4% more accurate, check out the Atmosphere Hawk. It's an instrument we make which makes your experiments that much more accurate. And the reason why is because the density of air changes every day. Like if you were to walk into your wind tunnel and do tests in the morning, and then you come back after lunch, the density of air will change. And we don't really, well, most aerodynamicists don't. I do, but most aerodynamicists don't log the density of air as they're doing their experiments. That's a major problem because when you come back, you get this 2 to 4% error. And between days, weeks, months, seasons, it changes even more than that. 10%, 15%, even more, 20% is common. So you're getting this error in the density. It doesn't stay constant. It's not 1.2 kilograms per meter cubed all the time. It changes, it fluctuates. For example, right now when I'm talking into this microphone, I've got my Machine Hawk actually, and I can see that the density of air is 1.18 kilograms per meter cubed in this area that I'm in. So that's not 1.2 kilograms per meter cubed. That means if I were to do experiments and I were to assume 1.2 kilograms per meter cubed, my experiments would be wrong. And if I were to use that data to then go validate CFD, it would also present problems as well because the CFD that I am doing, I'd probably assume 1.2 kilograms or 1.225 kilograms. So my experimental data, which I'm using to validate, is different. So the Atmosphere Hawk gets rid of that error for you. And you can find it in the link description. And I'll see you in the next podcast. Peace, amigos.